What we're going to do this morning is have a look at electric circuits, voltage, current, resistance, all that kind of stuff. Okay. It's not a very nice topic. No one likes this topic particularly, but I reckon it is worth. I always think marks in these questions are worth double because many people who are taking your exam are not going to get these questions right. Okay. It's not like getting question 1A right, which everybody in the nation gets right. Okay. So although electricity is horrible, it is worth having a go at because any marks you get here kind of help to move you up the ladder, as it were. Okay. Now, most important thing with electricity is to understand what's going on. And of course that's really difficult because when you turn something electrical on, the wires just sit there, lights come on, things happen, but what the electricity is actually doing is really difficult. Okay? So what I'm going to do this morning, because we've got a little bit longer than you'd have in a normal lesson, what I'm going to do this morning is try and give you a mental picture. Alright? So when you look at a circuit, you can visualise what's going on. If you can do that, as you know from any other area of physics, you can work stuff out. Alright? Trying to learn electricity by knowing each kind of circuit and stuff like that is just never going. It's never going to work in physics anyway, is it? All right. Physics is about here's a situation not quite the same as what you've seen before. Can you use your physics to work stuff out? Okay. Many people can't in electricity because they don't really have an image of what's going on. Okay. And it's not like forces pushing and pulling where it's like really obvious what's going on. Electricity is just invisible stuff in wires. Okay. The first one I'll mention is to think of electricity like water flowing along a pipe. Okay, that's quite a popular one. I was certainly taught that one at school. I'm afraid to say, even in the 21st century, you still find that in textbooks, you still hear people going on about it. If you are determined to absolutely never understand electricity, that is the one for you. All right. Thinking of electricity, and it's in the language, the word current, electric current, it sounds like water flowing along. That's the first thing. If you've ever been taught that or you've ever read about that, that is absolutely stone cold wrong, okay? It's not just me saying I don't like that way of teaching. If you think about electricity like the flow of water, that isn't how electricity works. Despite the fact the words seem to line up, words like current, that is absolutely wrong. If you do nothing else in this morning's session, go away knowing that that isn't never going to work for you, okay? Let me give you a way of thinking about them that will, all right? And the first thing we're going to do is just to draw a very simple circuit, a battery, and a bulb. Couldn't be easier, okay? And to think about what's happening, all right? Now, first thing to realise is there are two things happening in a circuit, okay? If you've ever wondered why we have current and voltage, why don't we just have how much electricity? And the answer is because there's two things happening. We need two quantities in electric circuits because there are two things happening at once, okay? Firstly, as you probably know, there is electric charge or electrons. Yeah, there's electric charge or electrons moving around. If you're an electron in a piece of wire, then if it's a piece of wire, it's made of metal, that means you're free to move. So you're an electron, you're in a piece of wire, you're free to move around, you're not stuck onto an atom particularly, and somebody makes one end of the circuit plus and the other end minus. Remembering electrons, of course, are negative. It's pretty obvious what's going to happen, isn't it? You're going to get pulled towards the plus side of the circuit and pushed away from the minus, okay? So electric charge or electrons going round, okay, you probably knew that already. But there's a second thing going on, all right? If you think about this circuit, when you turn it on, of course the bulb's going to give out light, heat. If this was a motor, it would give out movement, and all those things are forms of energy, aren't they? All right? And if you think what's happening in the battery, although again, language is against us, think about a battery, it's gone flat. All right? If you connect to a light bulb, no light comes out. Connect it to a heater, no heat comes out. Connect to a motor, there's no movement. What is it that a flat battery's run out of? Energy. It's run out of energy, hasn't it? All right? So there's energy in the battery and it's being transferred to the bulb. All right? So you need to draw like a big arrow there with energy. All right? In an electric circuit, there are two things happening. There's electric charge going round, and there's energy being transferred from the battery to the bulb. That's why if I leave this circuit on for a long time, the battery will eventually go flat, which means it's run out of energy, and the bulb will go out. All right? It's as simple as that. So there are two things happening, and this is why electricity is difficult. All right? Electricity is difficult because, like patting your head and rubbing your tongue at the same time, you're trying to juggle these two things at the same time. All right? If you think about electricity in this way, you'll start to get the right answers. Okay. First of all, the electric charge going round, we need something to measure that, and that's called current in amps. All right. If the electrons, can you imagine the electrons whizzing around really fast? That would be a big current. Electrons going around really slowly, that would be a low current. Okay? Now, how much energy is being shifted? That's measured using something called voltage in volts. All right? If there's a huge amount of energy for each electron, that's called a high voltage. If there's hardly any energy, that's called a low voltage. All right? So if we've done nothing else this morning, hopefully you can see why we have two things. All right? Why are there two ways? If you say, you know, how much electricity is going around this circuit, that's not a very good question. You end up having to talk about, well, there's this much current, that much voltage. Why are there two things? It's because there are two things happening. The current goes round, the charge goes round, and the energy gets transferred. Okay? Is everybody happy with that so far? Okay? Now, what we can now do is get a proper picture of what's actually going on. Okay? So we can use that idea, as I said at the start, we can use that idea to give us like a mental model, all right? A picture in your head of what's actually going on. Let me draw the circuit a bit bigger, okay? Now, if you think of the electricity moving around as water, that's a very, very bad way of thinking about it, all right? Because if, for example, if the water stopped, then it would lose all its energy, and that isn't how electricity works, okay? How can electricity that isn't moving still have lots of energy? What do we call that kind of electricity? Electricity that's not moving. It's not current. Exactly. It's not current electricity, static electricity. All right? The water model, as it's known, is stone cold wrong because it suggests static electricity wouldn't have any energy, and that's rubbish. Okay? So, let's have a look at a way that will work. All right? Let's imagine the electrical charge is like little railway trucks. Okay? Think of them as like little trucks on a freight train or something, and they go through the battery, they come out the battery, in they go, they travel around the circuit, they get to the bulb, presumably, they leave the bulb, and they come back round. Okay? So you can think of, you with me? You can think of the electricity going around. Do not think of it as water. Think of it like a little railway train. That's all very well in terms of current, but let's talk about the other thing that's happening. There's energy coming out the battery, energy going into the bulb. Let's imagine it's a 12-volt battery, okay? And if you're thinking this is the point where it starts to go wrong, when they ask you what's the voltage here, what's the current there, what happens here, this is really easy. Again, you've got to be able to picture what does that mean. When you see 12 volts on an exam paper, you've got to think in your head, what's that telling me about the electricity? It's really simple. How many joules of energy do you think there are in each truck? 12. All right. That's what 12 volts means. It means there are 12 joules of energy in each truck. Okay. You might have learned that voltage is the amount of energy per charge and wonder what that meant. It means something really simple. All right. How much energy does a 12-volt battery put into each truck? It puts 12 joules of energy. How much energy does a 3-volt battery put in? 3 joules of energy. It's as simple as that. Okay. So, how much energy will they have? Think of the little glowing lumps of energy in the trucks. When they leave the battery, all right, they've got 12 lumps of energy. Okay, 12 joules of energy. What happens to them in the wires, particularly in exam papers where the wires are perfect? The wires just act like railway tracks. Okay. So, how much energy will they have when they get down here? 12. It will be 12, won't it? Okay. So they're still going to have 12 lumps of energy. Okay. Trucks here, now this is the tricky bit, when trucks go back to the battery, this is like the fundamental law of how trucks work, okay? They have to go back with 0. All right, we can talk about why later on. For the moment, just take that for the way this game works. The way the truck model works is they must go back to the battery empty, okay? So, how much energy will each truck give out in the bulb? 12. Simple as that now. So, a really good picture to draw, if you're jotting this down, is out of each truck comes 12 joules of energy, okay, which leaves these trucks with 0, okay. Now that seems a bit of a daft idea, little trucks going round, like a little delivery system, okay, but you've made an important step. If you can look at an A-level exam question and you know, you get people who do this and they draw little trucks, you with me, they just draw a truck here and a truck there and just keep a track of how much energy. That will allow you, because that's how electricity works. It is to do with charge moving round, and it's to do with that charge having energy, which it gives out somewhere else in the circuit. Okay? Now, you might be thinking, this doesn't look like an A-level question. I couldn't write this nonsense that he's just told us. I couldn't write that in an exam. So let's try and relate this to current and voltage. Let's turn this into a proper exam question. Sort of thing they might do, they might put a couple of ammeters in, okay, and they might say the current here, let's say, is 3 amps, and they ask you what the current is over here, okay. Many people want it to be less than 3, all right. In your mind, you just think, well, electricity comes out of here, some of it's used up in the bulb, perhaps all of it, and then it goes back here, okay. First thing to understand, again, it's all about having a picture in your head. First thing to understand is what an ammeter is, okay? An ammeter is a bit like a little turnstile, like when you go on the underground or something, like the ticket barrier, or you go to a stadium or something. It's just like a little turnstile, all right? It counts numbers of trucks. So in an exam question, when you see 3 amps, again, if they just like numbers to you, you'd be better off doing another question, okay? 3 amps means, so this is the little picture you need to have in your head, okay, is 3 trucks going past per second. That's what 3 amps means. It means there are 3 trucks going past every second, okay? And obviously on this model they will be loaded up with their energy, okay? Now 3 trucks per second come along here, okay? They come into here, they give out their energy. If 3 trucks per second go into the bulb, how many must come out? 3. Many people think, oh, hang on, there's energy being given out. Very important. As I said, this model of electricity is all about separating voltage and current. Voltage and current are different things. They look at totally different aspects of the circuit, and they're independent of each other. So if you naturally thought, well, some electricity is being given out here, so this will be less than 3, you've got the right idea, but what you've just thought in your head is to do with voltage, as we're going to see in a minute, all right? Current is just to do with number of trucks per second. The 3 trucks per second go in here, loaded up with energy. The 3 trucks per second come out of here. But if you're an ammeter, you're not interested in that. What's this ammeter going to read? 3. It's 3, isn't it? Because, and if you're thinking, why on earth is it 3, think what's going to happen. If you're this ammeter, you're going to see 3 trucks per second going past, okay? You can't lose trucks. You can't have trucks disappearing, like 3 trucks going, but only 2 came out. You with me? That doesn't work. What is it about the electricity that the bulb uses up? The red glowing stuff, it's the energy, isn't it? Yeah? It'd be really funny if bulbs actually used up the electrons, if they actually used up the trucks. Because you'd plug things in, and they would start eating the wire, wouldn't they? You with me? So remember, the trucks are the electrons. If I could be bothered, I would draw trucks all around the wire all the time. All right? There are trucks in the wire all the way around, and they're free to move. That's why we use metal for electricity. Is because it's got electrons or little trucks all the way around. Okay? So this one is going to come out with 3 trucks per second. Now these 3 trucks per second going back here will make this ammeter read 3. And there is a difference. The 3 trucks per second that this ammeter reads and the 3 trucks per second that this ammeter reads, these are empty and those are full. What difference does that make to an ammeter? Nothing at all. All right? So this reads 3, that reads 3. Where could I put an ammeter in that circuit so it didn't read 3? Exactly. That's a trick question. Anywhere in this circuit. We've just learnt that current in series is always the same. You might have learned that and wondered why it's true. Yeah? If you can picture why it's true, you'll be able to deal with questions that look a bit different to the ones you've done in practice papers. All right? If you don't, you're going to struggle. Okay? So that's how current works in this circuit. Now voltmeters are a bit different. Let me put a voltmeter in. Voltmeters, as you probably know, but may have wondered why, voltmeters always go in parallel. You don't connect them like a little turnstile. Well, think about it. It's a turnstile. It's no good going to the train station. There's a turnstile over there, and everybody just walks past it. Are you with me? The turnstile's got to go in front of the passengers, doesn't it? The people have actually got to go through it. So this is why, if you ever wondered why, ammeters have to go in series, all right? Because they're like little turnstiles. They've got to be pushed round by the electrons. They've got to count the electrons that go past all the trucks. Voltmeters are different. They go in parallel, okay? But the way a voltmeter works seems a bit strange at first, but actually makes a lot of sense. What a voltmeter does is, with its two little legs, it grabs a truck. It's kind of a sampling process, all right? Imagine you're on the Jaffa Cake production line in the factory. You with me? You would just grab a couple and check they're okay. What you would do is it picks a couple of trucks at random, wherever you've connected it. It looks at this truck and discovers it's empty. It looks at this truck and discovers 12 lumps of energy. And then the voltmeter does a little sum and tells you the difference. Now in this example it's just 12, but we'll see later on it doesn't have to be that. Alright, so a voltmeter tells you the difference. If you were thinking, oh, perhaps the voltmeter just tells you how much energy in each truck, you could do that, but the amount of energy in each truck is called potential. How much, if you just picked a truck at random and said, you've got 12 lumps of energy, that's a potential of 12 volts. A voltmeter is telling you the potential difference. Get it? You ever wonder why in textbooks they still say voltage brackets potential difference? You just think, oh, that's an old-fashioned term. Potential difference, that's what voltage is. It's the difference in potential here is 0, potential there is 12, potential difference, or PD, is 12 volts. Okay? If I put a voltmeter here, are you with me? This one reads 0. Truck here would have 12. So again, this one reads 12. Okay? I always want this one to be minus 12 because... Other way around. Yeah. In this one, energy's going into the circuit from the battery. The battery puts the energy into the circuit, doesn't it? Yeah. This one, the bulb takes the energy out of the circuit. All right. I always want to call that plus 12 and minus 12. Okay. Now let's see if you've understood this. Let's put a voltmeter there. Never see that as an A-level question. It's a really good way of checking you've understood this bit.
0.
It's going to read 0, isn't it? All right. What's the potential here? If you grab a truck here, it reads 12. And if you grab a truck there, it reads 12. Exactly. 12 minus 12 equals 0. Now you might think, well, why does it do that? It's a bit of a mad thing to do. Voltmeters, remember, voltage is all about energy flow. All right. Voltmeters tell you when there's energy coming into the circuit and when there's energy flowing out of the circuit. Between here and here on the railway line, how much energy leaves or enters the trucks? Nothing. All right? So what's a voltmeter telling you? It's telling you about energy flowing in or energy flowing out. It detects energy flows. That's a good way of thinking about it. All right? On the water thing, it measures how hard the push of the water. All right. Voltmeters actually tell you, is there energy coming in, energy going out, or neither. Okay. Happy so far? Right, good. Now, I've got some more good news, which is there's only two types of circuit. If you can picture what's going on and understand what an ammeter and a voltmeter do, then there's only two types of circuits, series and parallel. All right. So this morning, if we can understand how to use the truck picture to solve problems to do with series and parallel circuits, that's it. Even at A-level, there isn't anything else you can do. And resistance is just nonsense anyway, so that won't take long. Okay? No, but seriously, the two important things are voltage and current. If you understand voltage and current, then you understand what the electricity is doing. Okay? Resistance we can deal with a bit in a moment. Okay? Let's draw ourselves then a series circuit, and let's make it look a bit more A-level-y. Let's have, again, 12-volt battery. And let's keep them the same for the moment. Let's have two light bulbs, both the same. Okay? Right, when you practice this, you get a bit quicker because obviously you draw one truck at a time. So that truck goes in with 0. That's the way the trucks work. It's a 12-volt battery, so 12. And that's it. This one's going to have 12 lumps of energy. Doing the different colours for no good reason. Draw the trucks, here they are. Okay, how much energy will there be in this truck when it arrives here? 12. That's it. Now, many people want this to be the first bulb, so it takes more, it takes all, or just a bit mad, really. Batteries plus and minus. Electricity goes plus to minus. But actually, that's a bit mad, isn't it? Because the trucks are actually electrons, they're negative. If you were a little negative electron in a wire, would you go plus to minus? You wouldn't, would you? Why do we talk about electricity going plus to minus? A couple of French guys in the 18th century guessed, basically. A lot of electricity, remember that first circuit I drew, battery and bulb? The battery and the bulb were separated by about 100 years. The first battery was invented about 100 years before the first light bulb. So for a long time people had batteries and they would like electrocute animals in there, put them in the mouth and stuff like that. Frankenstein, remember the film? Yeah? People wondered if you could get bodies going with electricity because the battery spent 100 years with nothing to plug into. Okay? A couple of French guys guessed. They decided that electricity must go plus to minus. And you may say, how stupid were they? Because actually we know electricity is electrons and they're negative. Yeah, that's great. That was discovered in 1900. All right? So 130 years later we discovered the electron. But we still have this stupid idea, electricity going plus to minus. Actually, electrons go minus to plus. Actually, they don't move very much. And alternating current, that's bonkers. Very importantly, if you think of this as the first bulb or that as the first bulb or anything like that, then that's not right. All right? If you think of electrical circuits, there's a posh name for this way of getting electricity wrong. If you have a sequential view of circuits, if you analyse circuits like first bulb, second bulb, third bulb, you're going to get the wrong answer. Okay? I don't help actually, because I keep drawing this little train like Thomas the Tank Engine, sort of setting off from the first bulb and journeying round to the second one. Where ought I to draw trucks? I really ought to draw them all over. Yeah? Where are their trucks? Where are their electrons? Everywhere in the wire. Okay? A nice way to think about this, if we had the time we'd perhaps do it, is imagine we had a big metal hoop. It would be like a hula hoop, big metal hoop. And two of you stood over there and held it, and I hold this bit, I'm the battery and you're the bulbs. All right? We all hold on to it, and I decide to move the hoop. Which person's going to feel the movement first?
At the same time.
Exactly the same time, aren't they? All right? So although my little truck picture doesn't help because I'm too lazy to draw all the trucks, remember the train is like a massive train that's so long it connects to itself. Are you with me? There are trucks all the way around all the time. As soon as the battery pushes the first truck out, in comes the last truck. So the battery, and this is a bit of a mad way of thinking about it, the battery knows about the whole circuit instantly. The instant you turn it on, the battery knows about the whole circuit. It doesn't go, the train's going to go, ooh, I'm surprised to find this bulb here. Doesn't help my truck picture way of drawing, but actually the battery knows about the whole circuit right from the start. So you're driving the train, you've got 12 sacks of coal in each truck. You've got 2 bulbs to go to, and they're both the same. So the only thing you can do is to take 6 out of that one and 6 out of that one. Truck here will have 6. On to there it will 6, gives out 6, gives us 0. Okay. If you put a voltmeter across here, it will read
6.
Because
12 minus 6.
12 minus 6. 12 minus 6 is 6. This one will read 6 as well, but because
6 minus 0.
6 minus 0. Okay, so that's how voltage works. If the current here is 24 amps, what's the current over here? 24 amps. Yeah, it's going to do it. Okay, so that's a series circuit. It's got 2 things in. Well, it's easy enough to do that with 3 or 4 or 5 or something, and you can see the voltage gets shared out. Okay, we are eventually going to fill out a big table. Okay. This is the whole of electricity. If you can do this table, you can do anything. There are only series and parallel circuits. And the only things you need to understand are voltage and current. Okay? Well, we've done some of these already. Current in a series circuit is always the same, isn't it? So current in a series circuit would be the same everywhere. Okay? Voltage in a series circuit, 12 becomes 6 and 6 is shared out, isn't it? Yeah? Can I have 12, 6 and 7? If I put 12 lumps in, can I take 6 out of here and 7 out of here? No. What law of physics would I be breaking? Conservation of energy. Conservation of energy, alright. So voltage in series circuit is shared out. Well, it must be, because voltage is to do with energy. Okay? Current is the same everywhere. Well, the trucks are electrons. And one thing a circuit doesn't do, it doesn't use up the metal. You with me? You've got the same number of electrons. That's why you say you recharge your phone battery. Phone battery's gone flat, so I need to recharge it. Put more electrons in. Yeah? It's not right, is it? The chemicals that were in the battery that are no longer able to put any energy into the electrons, but the number of electrons in the battery is exactly the same. So words like recharging don't help. Okay? Now, let's make this a bit more tricky. Let's have a 12 volt battery. Let's have 2 bulbs, which are different to each other. A bit scary now. Now, all I'm going to tell you is this bulb is twice as good at taking energy as that one. This bulb can take energy twice as quickly as that one. How can we share out the 12 volts now? Because 6 and 6 won't do. Yeah, that one's going to have to be 4 and that one's going to have to be 8. Yeah, remember, voltages get shared. Alright, at GCSE they're always the same, aren't they? So if you had 3, they'd be 4 volts each or something like that. At A level you could potentially, at A level potentially you could have, there are not many jokes in this and that was it. Do you see the idea? You can have 4 and 8 because it's the 12 again, you're sharing out the energy. Alright, trucks come out with 12, 4 off there, 8 into here, 8 out of there, 0 back round. Okay. Let's now, you might be thinking, when are we going to get to the A-level questions? Let's do this then. Here we go. Let's do something like that. Let's draw it like that. Very, very scary. Look at that. The battery's at the side, not the top. Whoa. Terrifying stuff, all right? You'd be surprised. They haven't told us anything about these 2 resistors, except this one is twice as good as that one. Okay? How's the voltage going to share out?
84.
It's going to be 4 volts across there, and that's going to be 8 volts across there. Okay? We give this type of circuit a very scary name. It's called potential divider. Okay? Potential divider, that is a potential divider. Alright? You're not allowed to say you can't do potential dividers. That is a potential divider. That is the same thing. That is exactly the same circuit. Okay? Very importantly, we're starting to see how resistance fits in. You may have been told resistance is how difficult it is for electricity to get through. It's gibberish. The bulb's really difficult to get through, so there are fewer trucks coming out. So the trucks come out more slowly. It's just nonsense. Resistance is possibly the worst named thing in physics. In fact, it's so badly named it isn't really a piece of physics. We'll come back to resistance in a moment. For the moment, though, resistance is the ability to take energy. Whatever you've been told about resistance in the past, forget it, because it was rubbish. Resistance is the ability to take energy. Let's go back to this circuit. How much energy is taken out in that piece of wire? How much energy gets taken out of the trucks in that piece of wire?
0.
0. How much resistance has this piece of wire got?
0.
That's it. Wires in exam questions always have 0 resistance, don't they? So you know this already because 12 come out of here. Think of the railway line, they chug along here, they've still got 12. What you're assuming is that this piece of wire has 0 resistance. Why is the bulb able to take energy out? Is because it has resistance. If you get a moment over the holidays, look up the discovery of the light bulb, and it's really difficult. If you get a thin piece of wire and you put electricity through it, it's metal. The electricity just goes through and does nothing. What do you need a bulb to have if you want the electricity to give up lots of energy as it goes through and make things bright? You need it to have resistance, don't you? All right. That's why old-fashioned light bulbs, the wire is very, very thin. It's very, very long. It's made of a wire that's not a brilliant, a metal's not a brilliant conductor to give it resistance. Okay. Resistance is the ability to take energy. All right. So if you say this is R and this is 2R, E hits the potential divider. Couldn't be. It's like a cake eating contest. There are 12 cakes, 2 people, one can eat cakes twice as fast. It is that simple. All right. Don't think of resistance as how difficult or how much it slows the electricity down. Absolute nonsense. Okay. Resistance is absolute nonsense actually, but this is the way to understand it in terms of circuits. If you've got resistance, you can take energy out of the trucks. If you haven't got resistance, you can't, just like the pieces of wire. And if there are 2 of them with different resistances, they'll take the energy out in proportion. Okay? Right, let's draw a parallel circuit then. Let's have our battery. Light bulb 1, there we are. And light bulb 2, so this is the bit nobody likes, the parallel circuit, very strange. Okay? Now, parallel circuits are the easier ones. You might think that's nuts. Series I can kind of do. I think probably no, you can't. Parallel is the difficult one, all right? Let's see what's happening. Now, imagine this is your exam question. If you've got an exam question, you can do worse than start drawing little trucks. The minute you get a circuit and think, eek, I can't do this circuit, start drawing the trucks on, all right? If you can work out what the trucks are doing, and you might be thinking in the exam, I can't write down about trucks. Well, I'd say two things there. One, I can easily tell you what the trucks actually are. They're not actually electrons. And the second thing is they never ask you. The level of understanding of electricity you need to pass your A-level is really, really low. The way you interpret that is to look at the questions and think they're really, really difficult. Well, for that reason, the level of what you actually need to do to solve A-level questions on circuits is really low. All right? If you go into the exam and you can actually picture what's going on, these are absolutely open goal marks. They are marks waiting to be taken. Okay? What you actually have to do even the most difficult circuit at A-level is not actually very hard if you've got the right mental picture. Okay? Now, what I suggest is we have, say, 2 trucks coming out. Obviously, I can draw any number of trucks. There's trucks everywhere, so let's draw a couple coming out. Trucks come down to here where things get interesting. Obviously, because this wire has no resistance, nothing happens, the energy stays in there. Okay. Now, it gets to this point in the circuit. And this really is just like a set of points on a railway track, all right, where 2 tracks split up. Now, the 2 routes are the same, so one truck might go that way, and one truck might go that way. Imagine, like a train maybe, where the first 4 carriages go one way and the train splits up at the station, so the first half goes one way, the second half goes the other way. What effect will that have on the amount of energy in each truck?
Nothing.
Nothing, all right? So the trucks come along here, and this one is still going to have 12. It's almost like a zip, the teeth of a zip, like that. Can you imagine the train literally unzips? The first truck goes that way, the second truck goes that way, third one that way, fourth one that way. Get the idea? All right. So think of the train literally undoing it like, one truck goes one way, one goes the other, and so on. Okay. Now, this truck gets to here. It's going to give some energy out to this bulb. How much energy must it have when it leaves?
0.
Just look where it's going. It's going back to the battery. So rather surprisingly, this bulb has to get 12. Because a truck that comes along here, yes, its neighbours, the one in front of it goes this way and the one behind it goes that way. That doesn't have any effect on the energy. It rolls up here with the full 12. There's been nothing so far it can give its energy to. And in fact, after this bulb, there's nothing it can give its energy to. So the only thing that this truck sees is this bulb, so it gives it the full 12. What about its neighbour with 12 volts? It comes down here. It's still got its 12. Again, look, it's only been through wire. All right? Very importantly, when it comes out of here, watch. You see? It's going back to the battery. So this has to leave here with 0 again. All right? So what voltage does this bulb get?
12.
And we could, if we wanted to, put about another 50 bulbs on. They're all going to get 12. This is actually the easy part about parallel circuits, is that the voltage is the same. If you put things in parallel, they all get the same voltage. Look at these light fittings. There are 9 light fittings in the ceiling. They're all getting 240 volts. There are 2 wires, 2 wires, and 2 wires. They're all in parallel. All the plug sockets and everything, it's all in parallel, so they all get the same voltage. Okay? You don't want these 9 sharing out the 240 volts, so they all get some number less than 240. They're obviously all getting the full voltage of the battery or the power supply. Okay? Now, if you're thinking, well, yeah, okay, I can make this much easier for you. As I say, the way I've drawn this circuit, if I'd sat down this morning and thought, how can I draw parallel circuits to make them really confusing? That's the way to draw it. All right? If you want to find parallel circuits difficult, this is the way you draw them. Okay? And I must admit, I've always drawn parallel circuits like this. The guy who taught me physics at school, he drew them like that, presumably because his teachers did. And pretty much since the invention of electricity, in the English-speaking world, and in most of Europe, we draw them like this. Okay? This is a really stupid way of drawing a parallel circuit. And after teaching for about 20 years, I'm talking to a teacher from Japan, and I mentioned about series and parallel circuits. Parallel is much more difficult. And he said, well, in Japan, they don't draw them like this. All right? In Japan, when you're taught parallel circuits,
I remember drawing that.
yeah, it's not very common, is it? Most times you see
Yeah.
parallel circuits drawn like this. This is the way, you find this in very, very few textbooks now. Draw it like that. Why do both bulbs get the same voltage, people ask? Yeah. Why? Can you see why they get the same voltage? Well, yeah, because they're both connected to the same battery. What battery is that bulb connected to?
12 volt.
What battery is that one connected to?
12 volt.
Yeah. Many people look at this, and think, well, this gets 12, so that much gets less or something. All right? This is a very bad way of drawing parallel circuits. All right? Because it suggests, again, that this bulb might get less than that one. And the worst thing is, if you actually connect this up, this one will get a bit less, because, of course, it's got a bit more resistance in the wires, isn't it? All right? In exam questions, it doesn't, because the wires are perfect. So this is a very, very bad way of understanding parallel circuits. This is the way to understand parallel circuits. If you think of them like that, it's obvious that they both get 12 volts. That bulb is connected to 12 volts. That bulb is connected to 12 volts. Let's connect another one. There's the bulb. That one's connected to 12 volts. All right? The only reason I can think of why we do this is because, again, let's take the light fittings. We've discovered that parallel is a really good idea. It gives everybody the same voltage. Let's connect them up like this. So we'd have, let's suppose the power supply is down here. You'd have 2 wires to that light fitting, 2 wires to that one, 2 wires to that one, 2 wires to that one, 2 wires to that one. Can you see you're wasting an awful lot of wire, aren't you? Why don't you just have 2 wires to the first one, and then another 2 wires to that one, and another 2 wires to that one? This is a wiring diagram. If you could see the wires in the ceiling for these light fittings, that's exactly how they're connected. All right? You have a pair of wires to the first one, and then just take 2 wires to the next one, and 2 wires to the next one. So in the English-speaking world and in Europe and stuff, we tend to draw parallel circuits as a wiring diagram. That's great if you're wiring up the room, but in terms of understanding parallel circuits, they're a very bad idea. This is a much better way, and explains to you why. Yeah? Things in parallel get the same voltage, because they're effectively all connected to the same battery. Okay? Let's do the last one. Current in parallel. Let's put the ammeter in. Let's suppose that reads 2 amps. What does that mean?
2 trucks.
That's it. There are 2 trucks per second. If the train splits up, how many trucks per second will go along here? 1. So that'd be 1 amp. How many along here? 1 amp. So the current has been shared out. Yeah. That's it. Using that, you can do any circuit. Okay? However, I have one little drop of rain into your lives, which is called Ohm's law. Because you might be thinking, I've been told, there are 3 things in electricity: voltage, current, and resistance. No, there aren't. What else is there to understand about this circuit? You can picture the trucks going round, trucks splitting up so the current shares out, voltage being delivered so they've all got the same voltage. What else is there to understand about the physics of this circuit? Nothing. But you might be thinking, well, I've seen these in the exam and they're saying nasty stuff like what's the resistance? And ooh. So we've done voltage, we've done current, and that means we've done the physics of electric circuits. Okay? However, in the exam, you get asked about something rather bizarre called resistance. Okay? Let me tell you about resistance, because it's not a pretty sight. The best definition of resistance, I think, is the one given by the Borg in Star Trek.
It's just futile.
It's futile. Resistance is futile. Resistance is not physics. If you can picture in your mind, remember what I said at the start, what's happening in terms of current, what's happening in terms of voltage, there's nothing they're going to ask you. All right? We finished electricity. We finished the physics of electricity. We're now going to do a rather random piece of engineering. This is an experiment that a guy called George Ohm did in the 19th century, and what he did was to got some things, some crocodile clips, voltage and current, and he put some things in here, and he obviously took down, I'm sure you've done this experiment, voltage and current, took down some values, and he drew a graph of voltage against current. Voltage current graph you've seen before. And here are his results. You get all kinds of rubbish, okay? You get a random selection of stuff, okay? Something mostly when voltage goes up, current goes up is usual, but it doesn't necessarily go up in a straight line, it goes in all sorts of curves. Now, he was a man determined to have stuff named after him. So he looked at that, you and I would look at that and go, well, there's clearly no obvious connection, so let's leave it. And he said, well, look, this part of the graph is quite straight-ish. So here's Ohm's law. Voltage is proportional to current. Now, if you did that at school, you'd get told, no, it isn't. But he said, well, look, it is if you don't go to too much current. Low current. And people said, well, what about these things here? And he said, well, no, they don't work because they are what's known as non-ohmic devices. What's the definition of non-ohmic device? Something that doesn't obey Ohm's law.
Yeah. So you made some stuff up.
It's just rubbish. This is Ohm's law, voltage is proportional to current. No, it isn't. There's Ohm's law. If you point to things like, go home tonight, get the cat or something, do this experiment with the cat, you do not get a straight line. The point is, when you bring your cat results in and say, look at that one, that's not a straight line. If George Ohm was here, he would say, yeah, but it's a non-ohmic device. And the definition of non-ohmic device, anything that doesn't obey Ohm's law. The best science is science that's easily falsified. Yeah, some great philosophers of science have said, the best science is science which is easy to prove wrong. Newton's law of gravity is really easy to prove wrong. All you would need to do is to drop the pen and it not to fall to the ground, and it would be every second of every day in every physics classroom in the land, Newton's law, you with me, could easily be proved wrong. How would you prove this wrong? You can't. It's bulletproof. And that is a hallmark of rubbish science. Rubbish science is science like, aliens built pyramids and stuff like that. It's just impossible to prove wrong. All right? Anything that's impossible to prove wrong is usually nonsense. So resistance, just no. All right? There are some devices, like, to be fair to Mr. Ohm, the people who wired up this building used Ohm's law, and they got about the right answer. If you're using bits of metal and you keep the temperature down so you don't let them get too hot, then voltage against current is fairly straight. All right? This is characteristic of a useful rule in engineering. All right? And that isn't, physicists would be horrible at engineers, but actually, there are rules of thumb the Romans used for building bridges and arches, like how wide it has to be for a certain height and stuff like that. Did they understand the physics behind it? Not at all. Have they built bridges thousands of years ago that are still standing? Absolutely. Same thing with Ohm's law. It's really useful. Voltage and current for bits of metal that don't get too hot are fairly proportional. If you use this, you will get close to the right answer. All right? And for that reason, it is quite useful. Ohm's law and the idea of resistance is quite useful, but actually, what's it got to do with the physics of electricity? It's got nothing to do with it. Okay? How does the word help us? Resistance to the truck slow down? It's just nonsense. All right? Resistance is, can't emphasise this enough because you never find this in the textbook, it's the ability to take energy from passing trucks. All right? Can I prove to you resistance is voltage divided by current? If you're thinking there's a third thing in electricity, this voltage divided by current, I've got to get my head around, there absolutely isn't. You will see resistance mentioned in the exam, at which point you think, many people sat in the same exam will perhaps are thinking it's to do with slowing the water down. You're thinking it's the ability to take energy. Things that have resistance can take energy. The more resistance they have, the more good they are at taking the energy out. And that's how you do things like potential dividers and stuff. Let's just have a look at resistance. It's voltage divided by current, so it's volts per amp. Yeah? Which means a volt, remember, is a joule per truck. Yeah? You may have spotted a truck actually isn't an electron, is it? It's a little bundle of electrons, a little group of electrons, about 10 to the 19 electrons, called a coulomb, all right? When I do this with the lower school, I tell them it's an amount of energy per electron, and that's fine. If you try to do the maths of that, think how many electrons are moving around a circuit in real life, you just get ridiculous numbers, okay? So we don't count this is the thing I was talking about here. We don't have actually electrons going around the circuit. There's trucks. A truck is a big bundle of electrons, a coulomb's worth of electrons. Okay? So a volt is a joule per coulomb. An amp is a truck per second. Rubbed it off now. Do you remember? A truck per second for the turnstile. That's a joule per coulomb over a coulomb per second. So it's joule per coulomb over coulomb per second. What does that cancel down to? No, they don't cancel. It's a joule second per coulomb squared. So if you're thinking that resistance, no, because all my physics teachers told me I must learn about resistance, it'll help me understand the physics of circuits. No, it won't. You need to understand properly voltage and current, and that's it. If you're thinking I want to get my head around resistance, you're trying to understand something that's fundamentally a joule second, not a joule per second, that's a watt, isn't it? This is a joule second per coulomb squared. It's like cat's per ironing board squared, isn't it? It's just nonsense. What is a joule second per coulomb squared? The answer is nothing you need to worry your heads about. All right. The ohm, the unit of resistance, a volt per amp. The danger with resistance is you start to think that voltage and current are linked. Are you with me? Seriously, don't spend a long time worrying about resistance, because what you'll start to do is muddle up volts and amps again. Remember at the start we got some numbers wrong. It's because we were linking voltage and current. Voltage is the energy per truck. Measure with a voltmeter, it works in that way. Current, number of trucks per second. Measure with an ammeter, works in that way. And if you muddle the two up, that's when you start to make mistakes. So this is the reason I'm poking fun at resistance. Don't be thinking voltage and current are linked by something. No, they're not. All right. Seriously, that's how meaningful resistance is. A joule second per coulomb squared. Okay. Let's do two very quick equations. Okay. And then you can have a go at working something out. Okay. There are some equations to do with electricity. Power, voltage, and current. Power is voltage times current. You heard of that one? Yeah. That's easy peasy to understand. Let's have a light bulb here. Let's have 3 amps on the ammeter. And the voltmeter reads 4 volts. And the question is, I want to know how much energy is coming out the truck per second, because that's called the power. Okay. That looks like a complicated overall question, but it isn't. 3 amps, what does that mean if we're picturing stuff?
3 trucks.
3 trucks per second. 4 volts, what does that mean?
4 volts of energy in each.
4 joules of energy being taken out of, because it's a bulb, remember? It's taking 4 out of each truck. And here's today's question. How much energy does the bulb get every second?
4 times the 3.
Yeah. It's your birthday. There are 3 postal deliveries during the day. And each postman brings 4 presents. How many presents have we got at the end of the day? 12. So if I said to you, what's the power here? You would say 4 times 3 equals 12 watts. And you would be right just by thinking about it. Where was the 4? That was the voltage. The 3 was the current. That's why power is voltage times current. It's kind of obvious, isn't it? How much energy per second will be how many trucks per second and the amount of energy you take out of each one. Again, think of postman bringing you presents or something. Q equals IT. You've got charge equals current times time. Yeah? Why would that be true? Well, let's have a circuit. Let's have 2 amps flowing. And let's run this circuit for 10 seconds. Charge, remember, is trucks. And a truck is actually a little bundle of charge called a coulomb. 2 amps for 10 seconds. How many trucks? 20. How have you been able to answer that question so easily? Because you know that 2 amps means 2 trucks per second. So when it says how much charge is there, you know that you need to take the current, which is the number of trucks per second, times by the number of seconds, and that will give you 20 coulombs, which is the right answer. Why is charge equal to current times time? Well, because it would be, wouldn't it? Yeah? If 2 of them arrive every second, and that happens for 10 seconds, it's pretty obviously 20 trucks, and that's why charge equals current times time. Okay? So we've done current and voltage. We've done series and parallel, and that's the whole utter complete history of electricity. You can solve any A-level question using that. We've had a bit of a laugh at resistance, ability, you'll never find that in any textbook I've ever seen, it's the ability to take energy. It's nothing to do with anything you've been told about how difficult or anything like that. It doesn't mean there's a link between voltage and current. Keep them separate in your mind because they work in different ways. And we reminded ourselves what trucks are. There are coulombs worth of electrons. And we've seen why power equals current times voltage and why charge equals current times time. Okay? Now, let's put this all together and make up the most difficult question in the history of the universe. Okay? I reckon if we put that together, and let's turn this into the worst thing that could happen. If I'm a really, really horrible examiner, I might do something like that. Now, the good news is, if you can do that, you can do anything. There's nothing they can ask you in an A-level exam that's going to be harder than that. So let's make up some numbers, and this will go horribly wrong, I'm afraid. So let's go for those. Okay. Now, if this was an A-level question, they would structure this a bit for you. They'd say part A, work out this, part B, work out that. They'd kind of what's called scaffold it for you. They'd lead you by the nose a little bit through it. Okay? The one thing I would add into this, I think, is... Well, no, let's think what we've got. We have got the dreaded Ohm's law, haven't we? We have got that resistance is voltage divided by current. We have got Ohm's law to help us. And we've got the truck picture, which works in that way. Okay? Now, the problem is we don't really know anything to do with current, all right? And we can't share out this 12, can we? Can I convince you that there's going to be some voltage dropped across that resistor and some voltage dropped across that resistor? And if you're thinking, well, actually, that's two resistors, well, kind of, because, remember, think about it, a truck coming along here and a truck going through there, they must both drop off the same amount of energy. Can you imagine a truck that went through the top resistor and a truck that went through the bottom resistor? You with me? You can't get out of step, can you? You can't have some of the trucks coming back with 1 amp, 1 joule, and some coming back with nothing or something. So remember, this is a parallel bit. Remember what happens in parallel? So when the trucks go through here, let's picture it, the trucks go along here, they drop some energy here, they drop some energy, well, the ones that go through here drop a certain amount, the ones that go through the bottom drop a certain amount. Many people get very confused by the different resistances, but, I mean, let's make up some numbers. It comes out with 12. Let's suppose it drops 8 here. A truck that goes through the top here would have to drop 4. Its neighbour that went through the bottom would have to drop. Do you see? So I know we don't know the answer yet, but there is only that voltage. Don't be thinking there's the voltage dropped on the top one and the voltage dropped on the bottom one. Are they different because of Ohm's law? No. Parallel. All right? So a good way to think about this circuit is actually, it's this. It's a bit like that. All right? Although these two are in parallel, they're going to work like a single resistor. Okay? And this is the bit of resistance that you do need to know, because at the moment this circuit, which I think is too difficult for A-level, just giving it to you like that and say work it all out is too difficult. They would have to give you some scaffolding, so we're doing something really difficult here. The 12 volt, do you remember this one we did at the start of the lesson? Remember that one? This is what you need to have in your head. It's the same thing. Truck comes out, drops some energy across this one. The trucks go on and they drop some energy across here. And don't be worried about the fact some went that way, some went that way. It doesn't make any difference, it's parallel. Alright? So each truck drops some energy here, some energy between there and there. It doesn't matter which way they went. And then goes back. Alright? Let me introduce then a little piece of physics that you do need to know, which is to work out, some people call it the total resistance, I wouldn't call that the effective resistance. You need to be able to work out the effective resistance of two things in parallel. And as you might know, that's that one. Okay? Here's a little bit of stuff about resistance that you do need to know, but always regard resistance as just some handy rules to get the answer. This is not telling us anything significant about the physics of electricity. Okay? So, if I gave you this one, and I said this was 4 ohms, and that was 8 ohms, you'd be able to do it, wouldn't you? If I gave you those two, and said a 4 ohm and an 8 ohm, 12 volts across them, how much voltage across each? That would get 4, that would get 8. Okay? Why can't you do this one? Well, you know the resistance of the first resistor. Resistor 1 is 4 ohms, we know that. Resistance of number 2, that's more tricky, because between here and here we've got 2 resistors connected in parallel. How on earth do we deal with that? Well, this is the spanner that you take out your toolkit at this point. You need to convert this into a single resistor. Many people say you need to work out the total resistance. It's not really very helpful. What you need to do is to turn that into a single resistor that would have the same effective resistance. Why? Because it doesn't matter which way the trucks go. They're going to drop a certain amount of energy between there and there, just like the second bolt. It doesn't matter which way they went. Okay? So R1 times R2 is going to come out to something horrible probably. It's going to be 2 times 3 over 2, 2 plus 3.
Yeah.
Right over sum. 2 3s are 6, 2 and 3 is 5. That's not nice, 1.2, isn't it? 6 over 5. So in your mind, if you get this in the exam, what you need to do is to say, actually, this is a very simple circuit. It's just a 4 ohm resistor and a 1.2 ohm. Do you see? That, same as that. All right. Not if they say, what's the current through this resistor only, but we'll come to that later on. We can't do this circuit, we can't do anything with this circuit, because we don't know how the 12 volts is shared. That's the way to look at this. Why? Because we don't know the resistance of that. All right? The resistance of that bulb, keep this in your mind, is 4 ohms, because they tell us. The resistance of this bulb, well, it's a complicated thing. It's made up of 2 resistors. That's what this equation was invented for. All right? So in the exam, don't do that circuit, do this one. Okay? The 12 volts is going to get shared out. Which of these two gets more voltage? Yeah. The numbers are a bit stinky, aren't they? But do you remember the one we did at the start of the lesson? The R and the 2R1? Exactly the same thing. We've got to share the 12 out in the ratio 4 to 1.2. Did you do ratios in GCSE maths?
Yes.
Yeah, good. So, we need to split up 12. We need to give 4 portions to this one and 1.2 portions to that one. So we need to divide it by... Have you done this? 5.2? 12 over 5.2, somebody with a calculator? So 2.3 volts. Yeah? So the portion sizes will be 2.3 volts. This one is going to get 4 times 2.3. And this one is going to get 1.2 times 2.3. 4 times 2.3? Or 1.2 times 2.3?
9.2.
And
2.76.
2.8. Yeah? Numbers aren't nice, but it's the same idea, isn't it? Yeah? So this one's going to get 9.2 volts, and this one's going to get 2.8 volts. Yeah? So we've done this first bit. Let's suppose the exam question asked us for that voltage, 9.2. What does the 2.8 mean? Very importantly, don't draw it across either resistor. This is 2.8 volts there. Between that point and that point, any truck will drop 2.8 volts. It can go this way and drop 2.8 volts. It can go that way and drop 2.8 volts. Either way, it will drop the same voltage. Okay? Do we know the voltage across every resistor now?
No.
Yeah.
Yeah.
Yes.
Do you remember? Because we've worked out, when you see a circuit like this, if you ever do, think of that. Yeah? Think about the journey of a single truck. If you ever get stuck on a circuit, imagine you were a single truck, what would you do? You'd go through this one, you'd go through that one, you'd go through that one, and back. How many resistors have you seen? 2. Your neighbour sees 2. Don't look at this as a 3 resistor circuit, it really isn't. This is the place where you can drop some energy, and this is the place where you can drop some energy. The fact that some trucks do it that way and that way makes no difference. Voltage in parallel, remember, is the same. Okay? Working out current, again, this is where Ohm's law comes in quite useful. There's various ways of doing this. You could say, what's the total resistance of the circuit? 5.2. So the current coming out of the battery is going to be using Ohm's law. 12 volts over 5.2 ohms gives you with me? You could work out the current. Or if I said what's the current through this resistor, it's just going to be 2.8 volts across 2 ohms. What's the current across this resistor? 2.8 volts across 3 ohms. Yeah? Which of these will get the bigger current?
Top one.
Yeah, top one's got low resistance. I know we say that, but that just doesn't mean anything. But that's how it's going to turn out. Why does this one get a bigger current? Because they've got the same voltage. Both these resistors have the same 2.8 volts. So the smaller resistor will have the bigger current, the bigger resistor, the smaller current. If you add those two currents together, they'll equal the current coming through there. Okay? That's a bit of a horror, but again, just giving you that with no guidance at all, no A, B, C, D or anything, would be pretty much not something that you'd be able to do at A level. You'd need to give them some sort of guidance. Yeah? Okay? So that's the whole of electricity. If you can remember this table and you can think about why it's true, yeah? So your homework over the holiday is going to be, go back to some electrical circuits you thought you couldn't do, start drawing the trucks in, yeah? Start drawing in the truck. When it says this is 12 volts, you need to put 12 coming out, 0 going in. When it says this is 9.2, that means that's got 12 and this has got 2.8 or something. That's got 0. Do you follow? You need to start drawing trucks with their energies around the circuit. In proper physics terms, you're drawing a potential map. Yeah? And the voltmeter will tell you the potential difference. Okay? If you're thinking I might get an exam question where they ask me to write about what's happening, A, they don't, and B, if they did, instead of saying truck, you just say a truck is 1 coulomb of charge. If you talk about the energy in joules from each coulomb of charge, that's a top A-level answer, isn't it? Yeah? So replace the truck with coulomb of charge, and all the gibberish I've taught this morning would turn into high-quality A-level answers. Okay?